Welcome back. So now we want to talk about the probabilistic interpretation of linear regression. And for this, it's good to remember how we started the definition of linear regression. So we said that our targets, our values we want to predict, are not perfectly the output of our function, of a linear function. This is what we can't expect, right? But there's always like a small noise attached to it. We had this variation around the perfect line, for example, okay? And what we said is, for example, when we picked our noise as some Gaussian noise, some white noise, where we said, okay, it's a zero mean, right? Because we don't want that it's shifted around the line, but we just have some variance around this line in our data, right? So if here's the line, right, our samples are somehow with a zero mean around this line, okay? Good. So we have the prediction plus a noise. Where we picked here this precision, or this is like the variance term, and here we have the precision, which is called beta, which is just the inverse of this, okay? So equivalently, we can reformulate this here as just another Gaussian, okay? So instead of first sampling a zero mean noise and then shifting it by the prediction, what we can equivalently do is we just say the targets we want to predict are sampled from a Gaussian where the mean is our prediction, and then we have the corresponding noise, okay? So it's essentially just two different processes. Here we first sample the noise, right? This is again similar to this coin flip, by the way, right? So we sample the noise. Now the noise is sampled from a Gaussian, right? So it's sampled from a Gaussian distribution. So it's somewhere some real number, unlike to a coin flip, which is 0 or 1. So we first sample a Gaussian, then we shift it, so to say, by the value we have predicted on the line, right? And here we do it the other way around. We immediately shift the Gaussian by the corresponding mean. If you think about this here, let's say there's a second mean, and here was our predicted value, f of x, okay? So in U1, we sample from this red Gaussian and then shift by this value. So let's say we sample this value here, and then we shift it to the side by the same amount here as here, right? And the other one is we immediately shift the Gaussian and then we can sample this position. This is equivalent, okay? And this is what you see here. And now you see that this linear regression model is also just some random experiment. It's like a generative process, right? So we have here in this probabilistic graphical models view, we have, for example, some deterministic value parameter x1. This is like the input feature, right? We have the deterministic parameters w and beta, right? W are the weights, the parameters of the function, and beta is here this precision term. And this just makes up a Gaussian. From this Gaussian, we can sample the corresponding result. Okay, so the only randomness we have here is when we sample our regression target from this Gaussian distribution. Okay, so one more time, the parameters of the Gaussians is a predicted value, which depends on w and x. Okay, because w times x is our model, as we see it here, right? W and x and potentially the basis transformation, they form the mean here, so to say, and the variance is given by this beta. And all these here are the deterministic parameters, and then the only randomness comes from this, from the target. Okay, so here this is encoded gray because these are the observed random variables in our probabilistic graphical models. Here we don't have any hidden variables. So this is a simple probabilistic process of linear regression. And as you know from this probabilistic graphical models, this is indeed something like a generative process. Generative process means we can, intuitively speaking, really generate, simulate data, because if I give you a w, an x, and a beta, you can easily generate new y's by just sampling from this Gaussian. So how does this help us now? This helps us because now we can take the same approach as we did, for example, in this coin flip. Because in the coin flip, we generated, so to say, outcomes of heads and tails, right? This was here like the outcome of the coin flip. And what we did is we learned the parameters of our Bernoulli distribution, right? So this was our setting in the coin flip. We had here like the outcome of the coin is like a Bernoulli with respect to parameter theta, okay? This is what we have observed, the outcomes, and this is what we try to learn, the theta, the behavior of the coin, so to say. And now we do the same. We do the same that we want to learn now the other kind of parameters of our model. Okay, I mean specifically, as you might see here, we want to learn W and beta because X, of course, we don't want to learn X is a given data. Okay. So more formally, what we can do is, similar to the coin flip, we can write down first of all the likelihood function, the likelihood of with respect to y, so to say. Okay, so because y is a random variable, we can write down the likelihood with respect to y. And here it's just from the previous slide, it follows a Gaussian. And based on this IID assumption you have learned from before, we can here like factorize it. Actually, it's only the independence assumption because every result will behave differently. So it's not identical, but it's independent. So we can write here the product over these individual contributions. Okay, so the overall likelihood of y conditioned on the rest we have given, right? X, W, and beta. This is given, so to say. We can write down here this likelihood term. It's simply the product over every outcome over every target given the parameters we have at hand, so to say. Okay. So this is the assumption. We assume these samples are independent. And then, as I said, as before, we can now try to learn, for example, a maximum likelihood estimate. Meaning we can try to find the beta and the W, beta and W, such that the likelihood of this is maximized, right? The likelihood of seeing these targets, these values, right, the y values, giving these parameters, and of course given x again, right, because x is now additional input we have at hand. We don't have to learn it, but it's also not a random variable. This is just given this the input x. Okay, so this is our likelihood function of all samples, and we want to maximize it because we want to compute the maximum likelihood estimate. And indeed, this is now what we want to do a bit like in more detail, and you see some very nice results showing up here. So again, here's the task, right? So here's our likelihood function, and we want to find the optimal parameters, W and beta. And of course, as you know, we can do some tricks here. Because we're interested only in the argument here, the argmax, we can apply a monotonic function. We can apply the log, for example. Okay, this won't change the optimal solutions here. Okay. And of course, instead of doing a maximization, we can try to minimize by just having here the minus in front of it. Okay, so we are minimizing the minus version of this. This, of course, is also equivalent, as you can see, right? Maximizing thumb function is, of course, the same as minimizing the function mirrored, so to say. Okay, and this is now what we call the maximum likelihood error function here. Okay, so minimizing this function here is the same as finding the maximum likelihood estimate. Okay, so why do we put this into this minimization form? Because before we also talked about minimization, right? We talked about minimizing the least squares loss, and now we want to minimize this maximum likelihood error function. So we call this ML, maximum likelihood. So this is our error function, the negative log likelihood. Okay, so just as a term you should remember, right? This is the likelihood. This is a log likelihood, of course, and this is a negative log likelihood. And we want to minimize this negative log likelihood. This should be as small as possible to find good parameters. Okay, good. So now let's plug it in. So we have to plug in the assumptions we made about the distributions of our model, right? And the only assumption here was that, let's go back, that this here is a Gaussian, right? The prediction, the regression targets follow a Gaussian based on these two parameters. And this is just what we can now plug in. So here you see again this negative log term. Here you see the independence assumption. And here you see the Gaussian. Okay, so the target and the mean and the variance here. Okay, and now we can really just expand it, right? You can open any textbook. You see what is the definition of a Gaussian, right? It's here some constant, then we have the e to the power of something, right? So here specifically you see the mean, okay? And what was the mean? The mean was here this function, right? F is the mean of our Gaussian, and this f function was our linear model, right? So we have here this W parameter vector times the potentially transformed data. So this was the prediction of our model, right? So this here is this here, and here minus what we are observing, so to say. Okay, so this is really just plugging in the definition of a Gaussian. Okay, so where at the Gaussian we are, minus the mean of a Gaussian, and then scaled by the corresponding variance terms. Okay, so this is just plugging in. And now we do some kind of simplification or reformulation. So since we have here log and here product, we can take this out, right? So the product becomes a sum here. So this is what we did in this very first step. The rest stays the same. And then finally what we did is we expanded this logarithm, because a product inside of a logarithm becomes a sum. Okay. So what we end up with at the end is we have here this beta term. Then we have here sum over all data instances. And here we have already simplified it. The sum doesn't, the sum, so to say, the sum over the instance is not important anymore, right? For example, if you look at this term here, okay? So we're summing over this term, but this term does not depend on I, so we get an additional times n, so to say, right? We have a sum over a constant c, and the sum goes over n elements, so the result will be n times c. And this is why you're getting here this additional m, okay? From this term here, and that's all actually, right? So here's this lower part, and here's the upper part, okay? So just be careful, the square root becomes here this divided by 2, right? Because again, we have this logarithm, right? This is how it boils down to. But long story short, this is really just plugging in the assumptions we made about our model, about our probabilistic model, that it follows a Gaussian, okay? And then we have this solution, right? This is our maximum likelihood error function, so to say, which we aim to minimize, okay? So let's now really minimize it, right? So we'll minimize it first of all with respect to W, okay? This is one of the parameters we have at hand, the W. So we have here again this argmin as before, right? Here it's just plugged in from the previous slide. And now you see something interesting. Wait a second, this term here does not depend on W at all. So it's a constant with respect to W, and as you also learned before, these constants, they don't matter for the argmin solution. So on one hand, the constants which we are multiplying, right, they don't matter for the argmin, but here specifically also the constants we are adding, right? If you're maximizing a function fx plus 10, of course, the optimal, so the minimizer will be the same as just minimizing f of x, right? This offset by 10, this constant offset by 10 doesn't matter. So again, this constant term, it disappears. So what is left is really this first part here. Okay, this very first part, right, where we also get rid of this constant b here, right? This first part is what is left. And you already see what this is here. This is indeed what we just assumed in the previous part of the video. This is indeed the same as the least squares error function. The predicted value, the observed value, squared and summed over all data instances. So what this means is finding this maximum likelihood estimate of our parameter vector is indeed equivalent of solving the least squares error function. Okay, so maximum likelihood estimate is indeed the same as the least squares error function, meaning the assumptions we made before in the previous part of the video, they are not arbitrary. They really follow from the idea that we assume a Gaussian distribution of our targets. This Gaussian distribution then reduces, or we can reduce it to this maximum likelihood estimate, and this is equivalent to this least squares error function. These are indeed the same, and so we also then know what the solution of this problem is, right? So what is the optimal solution? We can just reuse what we learned before. It's this pseudo-inverse times the target vector, okay? So this is a very important result. Maximum likelihood estimate in this model corresponds to solving the least squares error function. So what is now the benefit of this probabilistic point of view? I mean, there are multiple, and I show you one specifically. So what we now additionally have, and I do this very quickly, is that we also have this beta, right? So if you go back here in our probabilistic model, you see that this model is affected by W and beta, here, the variance term. And a different beta, of course, changes how our results will look like. If you have here a very large variance term, then the points will spread around this line very strongly. If the variance is very small, they are very close to this line, okay? And this probabilistic interpretation now allows us now also to estimate this beta parameter, which we didn't have before in the optimization point of view, right? There was no beta involved. We just said, okay, here's a line, we do a fit. But now we have this beta, which controls here the variance. It controls, so to say, here the spread around the line. So we can do now, of course, exactly the same. We can not only estimate the W parameter, but we can estimate also the beta parameter. And how do we estimate it? We estimate it with the same principle by maximizing the likelihood. Okay, we're maximizing the likelihood, or here equivalently, we are minimizing this negative log likelihood error function. Okay, so we cannot only just minimize this function with respect to w, but we can also minimize it with respect to beta, giving us an estimate about this variance term. And also just quickly, how can we do this? So the trick is the following, and we did it already here on the slide. Since we already know the optimal solution for the w, right, which was here, we have the optimal solution for our w, we immediately plug it in, okay, because we know how it will behave. And then once we have plugged it in, right, we again write down our error function. This is what it is. You see here the plugged in optimal solution for w. And now we can take the derivative with respect to beta. And what you see is specifically, okay, here this somehow does not, I mean, it depends on beta here in this part. Right here is this beta. This does not depend on beta, okay? So we can take the derivative with respect to this, which is extremely simple here because beta more or less appears only in very simple terms, right here in this log beta and here in this linear fashion. So the derivative is simply this here. Okay, it's a simple term. It's like this this error residual term from before, and then this what comes from this log beta term. Okay, we can set it equal to 0, right? Because you know how to find the critical points. Technically, again, you have to check whether this is then really a minimum, which it is here in this case. And then we have again in closed form the optimal solution. Okay, so this beta, the precision. So here we have written it as a variance, as 1 divided by beta term, is really just simply this. It's the average, the mean residual, the mean error, so to say, right? Because again, here the prediction, here the observed, and here we just normalize it. So the beta corresponds to the mean error and mean residual, so to say, mean squared residuals. So we now have a nice estimate about our betas as well. So why is this good? Because now, if we get a new sample, right, we do not just have here this line, right? So if we think about like standard optimization point of view, linear regression, if we get a new sample, so let's say here's a function f of x, and we get a new input here, let's say at position 10, the only point we can get in standard, the optimization point of view regression is like we get an estimate here, right? So let's say this is 5, okay? So this is what we can just get in the based on the previous video. We plug in 10, we get out 5. Okay. So now we have a bit more. We also have this beta term, which we can compute it here, which tells us the result we have here. It's not only at in mean 5, but we have also a specific variance, meaning the result we can get is more like we get here a Gaussian, which is centered at the prediction at f of 10. Right? And it has a specific variance term, which might be some number now, right? Or which is the equivalent in this example, it's a Gaussian at 5 and a specific variance, let's say it's something like 0.1, for example. Okay? So this is what we are getting. Or illustratively speaking, we are not only getting here this simple point, but we are also getting here something like some variance around it, right? So if you want to like slice it, you will get here something like a Gaussian, which goes up and then down, right? So this is what you get, like a Gaussian. Here it's likely and here it's unlikely if you slice it here. But you get something like the variation around this prediction. You don't just get the mean, the 5, but you get also this variation. And this is a big benefit of this probabilistic point of view, that you also get something like an uncertainty around this prediction. If the variance is very large, right? If this is a very broad variance, then you might potentially not want to trust this prediction. However, if the variance is very small, then you might have a high trust in this prediction, okay? So this indeed, this precision or this variance term gives you an additional information how likely is the estimate and how much fluctuation you have, so to say, in this estimate. So one last point I want to mention here, which always comes up when we were solving this problem with this problem here. This is a rather technical point, but still I want to mention this. So what did we do here? One more time. So we assumed here this is constant and we got rid of it, right? But then also we somehow said, okay, this is also a constant. And you know, if you multiply by a constant, right, we can also get rid of it. This is what we did here, right? You see the beta is gone. But you could argue, wait a second, beta is not a constant, right? Beta is a variable we want to find. But the important point here in this derivation is that this here, this derivation holds for every beta, any beta you can pick. So pick beta equal to 10, or equal to 20, or equal to 300. In every of these choices, you will always end up at this point, at this solution, so to say. So you always find this solution. Okay. So whatever this beta is, the solution for the W will always be the same. Okay, so you can essentially really assume, okay, let's assume some beta, whatever this is. So this is a constant now. So you can do this step and you will always find this solution. Okay. And as we see, this solution does not depend on beta, of course, right? Because this holds for any beta, it always gets the same. And since we can do this, right, since this really does not depend on beta at all, for any beta you're getting the same, right? For any beta you're getting the same. As it turns out, you can now, of course, then also just plug in the solution you obtained before, right? Because it doesn't matter what beta we are doing here later, right? If we're now optimizing over beta, this solution will always be the same, right? Whether we are changing here this beta, right? When we're minimizing, we are essentially testing various betas, right? We are testing various betas here, but this term will always be the same. So it doesn't matter. So we can do this, what we just did, okay? So again, this is always a valid solution, and then we can plug it in here, and then we get this solution for beta as well. Just a technical point how to derive it. What you should really just remember, or at least remember from this part, is we get an additional uncertainty estimate about the variance and not only the mean prediction value. Okay. Good. So this was the, let's say, the standard probabilistic interpretation, and we have seen that MLE, maximum likelihood estimate, corresponds to least squares plus a variance term. Now, since we introduced this maximum likelihood estimate, I guess you all know how to continue, right? Because what you learned in this coin flip example, the standard simple posterior inference in the coin flip, is that the maximum likelihood estimate might not be the best solution. We can also do like a maximum a posteriori estimate, meaning we take our prior beliefs into account. We can use prior knowledge about the process, and then we can derive the posterior, and we can derive the maximum a posteriori estimate. And indeed, this is what we want to do here as well, right? Because we know that MLE might lead to overfitting, especially if we have only little data, right? We have these two coins which both tell you they are head, right? And then we get a weird estimate. And the same happens here, right? MLE might not be the best choice, so we do with the posterior estimate. How do we have to change our probabilistic graphical model now? It becomes only slightly different. Here again, we see our deterministic input as before. Here we see our beta parameter as before. The only change is here. Now we have an additional information or additional assumption about our W. The W itself becomes a random variable, right? Because we assume that W comes from some other prior distribution, right? That was the core idea of this posterior estimate. So we had an additional prior distribution, or which we here have written like this, which in the coin flip example, what I guess we call it theta and A and B. It's A and B, right? So in the coin flip, we said the coin follows a beta distribution. So here's beta, where the parameter itself follows some distribution, right? The parameter itself follows some distribution. It becomes a random variable, technically speaking, right? And here we do the same. The parameter vector itself, the one we are interested in, follows a random variable. It's a random variable. It follows some distribution, and this distribution encodes our prior belief, what we think about this parameter a priori without seeing any data so far. Okay. And now you see the nice benefit of this probabilistic graphical model view. You can really encode all these dependencies very compactly. Again, so you have some hyperparameter which controls your prior distribution. We will see later on what we assume here. Again, related to the coin flip where we assumed it's a beta distribution which was controlled by A and B. Here we assume some specific prior distribution on W. And then we have additional our variance term, for example. And we have our deterministic input data. And all these together, they form here our final prediction, so to say. So here the Y, for example, again follows follows a normal distribution where we have the mean, which depends on W and X, and we have our variance term. Okay, so this here uses all different information. It follows again a Gaussian. And now you see how this flow is, right? Which parameter affects which variable. This is why this probabilistic graphical model view helps you here a lot. Okay, so what do we need? What do we need if we want to do like a maximum a posteriori estimate? We have to specify this part here. We have to specify the prior. What do we believe about the parameter vectors? That's the main point here. And this is what we talk about later in a bit more detail. And then we see some nice results again. So here just, again, a quick recap what I just said essentially on the previous slide. So here we want to now derive the posterior distribution or the map estimate of the posterior distribution. So we want to ask something about W, so to say, giving the rest, right? Given the data, given the targets, given the beta, and given this alpha hyperparameters. And as you should recall from the previous video, this can be reformulated based on Bayes' rule into the likelihood term, which we actually already derived in the previous part here, right? That was our likelihood term. We have the prior, which we will specify in a second. And we have our normalization constant, which we're usually not interested in, right? Because we're doing this proportional view. So we have the likelihood from before, and we need the prior in a second. And here you see again the relation to what I already said with this coin flip. So we had specific data before. Before this X was our only data we have at hand, and this was the observed data. Now we have to be a bit more specific. We have now here two kinds of data available. We have the deterministic input data, and then we have the outcome of our experiment, right? Remember that this here is essentially like the input, some deterministic input, but this is the outcome of our random experiment. So this relates to the outcome of the coin flip. And this is what you see here in more detail, right? In the coin flip, we have observed here the X's, the heads and the tails. Here we are observing the Y's. Okay, the Y's are the ones which are the outcomes of the random experiment. The X is not the outcome of the random experiment. Okay, so X is here in the condition. So the likelihood is with respect to Y. And here the likelihood was with respect to the X's. Then we had this prior here on theta, on the Bernoulli, and here on the W. We see it in a second. And then we have the posterior here again with respect to theta, the parameter of the coin, and here again with W, similar. Okay. So this is the relation between these two models, but you see it's essentially the same, right? Again, just be careful with these terms because many times it's confused. So what means prior, what means likelihood? So I guess it's easier to look at this figure again. So the prior here is the distribution on W looking from this side, and then the likelihood here, we can compute the likelihood with respect to these observed variables, which are the outcome of our random experiment. And then the posterior is usually also then, for example, with respect to W. But most important, this is what I told you in the last videos, make sure that you mention what kind of variable you are talking about, right? So for example, posterior distribution with respect to this W, okay? To be not confused about what we mean actually. Okay, so what do we need, right? That was the question. What we need this prior distribution because the likelihood we already have. And what can we pick as a prior distribution? So one nice choice as this prior distribution would be to pick a Gaussian. And we pick here a so-called isotropic Gaussian, right? Isotropic means the variance in every dimension is the same and we don't have covariance terms. Or simply speaking, if you want to draw it, we have here like the zero center. So the Gaussian is like these circles, right? It's like this Gaussian distribution in a multivariate setting, right? It starts here and it gets flat in the 2D space, right? But it's always like circles, so to say, okay? So along every dimension, it's the same. Or if you want to draw it as a covariance matrix, so the covariance matrix is really like a diagonal matrix, which is here like this alpha minus 1, and here you have 0 and 0, okay? So you have only terms on the diagonal and the off diagonals are all 0, okay? That's an isotropic Gaussian. We pick it, as you can guess, for convenience, okay? So here's just the formal definition, what it means. Right here again, this normalization constant for a Gaussian. Here just the definition of a Gaussian, which has a 0 mean. This is simply some assumption we make. And you can look into any textbook to see what this multivariate Gaussian in general is. And here this zero-centered Gaussian. So why does it make sense to pick this, right? Why does it make sense to assume this, specifically zero-centered Gaussian? It makes sense because what you learned already is that high weights often lead to overfitting, okay? high weights lead to overfitting. And this prior now tells us we believe that the weights should be small, right? Why? Because we are saying it's a zero-centered Gaussian. So if you draw it in a one-dimensional plane again, right? So let's say here's our Gaussian, here's 0. If we have a Gaussian, which is zero-centered, and we randomly draw numbers from this Gaussian, of course they're most likely landing here and less likely landing at the end, right? Because here we have only low likelihood and here we have a higher density, okay? So here we get values more often close to the center and the distribution is over the weights, so we get weights more close to the center, more close to 0, okay? So this distribution prefers weights which are close to 0, which we know prevents overfitting. So this is why this zero-centered Gaussian makes a lot of sense to put as a prior distribution. This is what we believe or what we want the weights to look like, okay? So this is what we have seen and what we have discussed already on the previous slides when we talked about the standard optimization point of view, but we can simulate this, so to say, also in a probabilistic point of view. And then the second point is, and this is also what we did before, is we picked it because this makes our life much easier, okay, as we see in a couple of seconds. Okay, so now let's derive this maximum a posteriori estimate, and this is just simply now writing down all the mathematics. I recommend you to do this at home, again, to really follow these steps in detail. Here I will give you like a quick overview of what you have to do. So first of all, now we are no longer interested in the likelihood, right? But we are interested in the posterior distribution, posterior over W, okay? And we want to find the W which maximizes this probability, okay? The probability of the posterior distribution. This was the definition of a map estimate. So what is this? We do these two tricks. First, we apply the log, and then we can split the product into sums. So what we see is that this here, this posterior, can be decomposed in, not surprisingly, to 3 terms. On one end here, we have our likelihood term, right? The likelihood with respect to y, right? Then we have our prior term. Remember, we're in the log domain already. And then we have the evidence term, okay? So likelihood, prior, evidence. Remember, the evidence was in the denominator. This is why we have here this minus. And of course, the denominator does not depend on the parameter w, so we can already get rid of it here, right? This constant term doesn't matter when we talk about the argmax here. Good. So that was the first step. And last step, of course, what we can do is, again, we can flip the sign. We don't want to maximize, but we want to minimize. So what we now want to solve is another error function, so to say. We want to minimize the negative log likelihood and the negative prior, so to say, okay? So this is what we have here, and we call this the log posterior, or the negative log posterior, so to say. So this function here is our error function, which we want to minimize, the negative log posterior, okay? So this is what we want to do now. As before, let's try to minimize this function, okay? So let's look at it. Let's plug it in and let's see what happens. So here the first term, right? This was again the likelihood. We had this derived before already. We can plug this in here. That's this part. Just check out the previous slides. And then we have here the prior term. Also just check it out on the previous slide. Here's our Gaussian. This is a normalization constant of the Gaussian, and this is here from the exponent. So the e to the power of the term, right? This is just our prior term. Okay. And now we can just simplify it. We can regroup it, so to say. So here what stays is this first part, what stays is this part here, and the rest is constant with respect to w, okay? So here's no w, and here's no w, and here's no w, okay? So this is what we did here, and here essentially this is now observed. And now comes some assumption here, which we have written here before. So in this slide deck, we now really assume that beta is known and given, okay? Because otherwise now the calculation would become a bit more complicated. So in the following, we really assume that this parameter here, this beta parameter, is assumed, it's given. We don't want to learn it to make our life a bit easier, okay? So it's really a constant. And then we can simplify this equation even further. We can, for example, say, okay, we have here lambda, like a shortcut, which is alpha divided by beta, meaning we divide this here by beta, Okay, so this is divided by beta, so this beta disappears here. And here we have an alpha divided by beta, and this beta we call lambda, so we hit here a lambda. Okay, so this only is now proportional, right? Because we divided by beta, and beta, as said before, we assume it's given, it's a constant, so we can just do this, right? We can divide by this constant. So what we end up with is here like this proportional. Okay, so again, plugging it in, getting rid of all terms which don't depend on w, and then dividing by beta, and substituting this here ends up here. And this again should look very familiar to you. This is our rich regression error function we had before, because here we have our standard least squares loss, and here we have our regularization term, the penalty on w, right? So we want to make this w small, and we have here this regularization strings. Put differently, the map estimate is indeed equivalent to solving the rich regression problem, to solving regularized linear regression. Okay, so map estimation with a Gaussian prior, of course its assumption what distribution should we assume, corresponds to rich regression. So here again, here you see these two nice results, right? Assuming like the y's are distributed as a Gaussian, right? And the w is distributed as a Gaussian, we get this nice match that this probabilistic interpretation indeed corresponds to the classic optimization point of view of rich regression. So we see that this indeed again has a corresponding probabilistic analog in this probabilistic world using this map estimate, which is a very nice interpretation, which shows you again why this choice from before, which we made in a rich regression scenario, this we want to do regularization by adding an L2 penalty, that this indeed actually makes sense. It makes sense because we can find this corresponding prior. So not surprisingly now, and this is probably a nice homework for you, is if we pick here different regularization, so we don't use, for example, L2 norm, but let's say we want to use L1 norm, so the sum of the absolute values only, then you can also find corresponding priors which correspond to this kind of regularization. So this is a nice task for you. Think about which distribution here corresponds to here L1 regularization. Good. So now we have done these two steps. We can find the map estimate using a prior. We can just use the MLE estimate, just looking at the likelihood, and then we don't need a prior. But in both cases, we had to assume something about the distributions. So finally, in accordance to this coin flip discussion we had in the last week, we can of course now also compute the full posterior distribution. We are not restricted to these point estimates, right? Both are just point estimates. Both just find, where do we have a solution? Both just find a single estimate about the parameter vector. But as you know, we can also look at a full distribution about the parameter vectors. Again, be careful. What is the distribution over now? The distribution is over W. We want to find which parameter vectors are likely and what is the likelihood of these parameters. So for example, we could say, okay, some weight vector, like, I don't know, the weights are 1, 3, and 7. This is a very likely parameter vector. But something else like 0, 6, and -3, this is an unlikely parameter vector. Okay, so we want to have a distribution over the parameter vectors, which we call here the full Bayesian approach. Okay, so important difference only is that when we're looking at the posterior distribution, we do not compute just the mode, the argmax of it, but we want to really know the full distribution here. Okay, but the rest is as before. We have here the likelihood term, and we have here our prior term. So we don't derive this here now in technical detail. I will just show you the results, because otherwise the mathematics is quite lengthy. So what can we do, or what will be the result if we pick here the prior as before? So we pick this multivariate isotropic Gaussian. As it turns out, the result will be again a Gaussian. And you know already what we did here. We picked a conjugate prior, right? So since this was a Gaussian and we picked here a Gaussian, this will also be a Gaussian. Okay, so the Gaussian is a conjugate prior to itself. So the posterior distribution here will be a Gaussian. So again, what is this posterior? It's a distribution where we just have given our data, x and y are given, and we want to learn the distribution over W. Here's the result, by the way, right? So this is a specific Gaussian, which has a mean and a covariance structure as illustrated here. And as said, we don't derive it here, but I want to quickly discuss it, what the outcome will be. You can find the full derivation in the Bishop book, of course, if you want to. So, but let's now just discuss it a bit what this means actually, and what is really why this makes sense at all. So first of all, we see that the posterior is a Gaussian, right? So in a one-dimensional case again, it's like a Gaussian. And why is this now helpful? We know that the mode of the posterior distribution is our map estimate, right? So the mode of the posterior distribution is our map estimate. So here's our map estimate. And since this is now a Gaussian, we know what the map estimate is because the mode of a Gaussian is a mean. So this here is our map estimate, right? So this is W map because that's the mode of the Gaussian. And this is actually nice because here I haven't shown you the solution. And also in the previous part of the video, I haven't shown you the solution for the ridge regression. I just said, here's the error function. Okay, we want to minimize it, but I haven't shown you the solution of it actually. Right? We have done it for the MLE estimate with this pseudo-inverse, but not for the map. But now we have it, right? We have it because we know that the posterior is a Gaussian and the mode is a mean, and here it is, okay? And it's not too complicated, right? You see that we have here this beta term, which we assumed is given, right? Here we have usually our design matrix and the target, and here we have the covariance matrix, which is also rather simplistic. Just be careful here, it's an inverse, okay? So to find this covariance, we have to invert this part here, okay? But the benefit is now we have found a closed form estimate for our map solution as well. We can just compute this here analytically. Second point I quickly want to discuss is like a limit case. So we have assumed here a specific prior distribution, right? How the weights behave. So we can make this alpha vector close to 0. What does it mean? It means that we don't know anything about our W. So it's like this very flat prior we have seen before in the coin flip as well, right? A flat prior corresponds to know nothing about the distribution of the weights a priori. Okay, so the variance becomes very flat. So let me actually go back to make it clear, right? So if this goes to 0, right, and this is here the precision, so the inverse is the variance. So if this goes to 0, the variance goes to infinity. So the variance is very large. We don't know anything a priori about our weights, right? Because this is so broad. Okay, so why is this interesting? We discussed this before. If we have more or less like a flat prior, right, a very flat prior, then the map estimate becomes the MLE estimate. Because the prior doesn't play a role, so to say. It's more like here, it's like a constant, so to say, right? So the map estimate becomes the MLE estimate. So meaning what we should hopefully see is that if alpha goes to 0, the map estimate becomes the MLE. And do we see this? Let's look at this. Where do we get the alpha? So the alpha is here. Let's say alpha becomes 0 and this disappears, right? So in the alpha equal to 0 case, or alpha can't be exactly 0, but it goes to 0, this sigma inverse becomes simply beta transpose the design matrix. Or if we don't write it in the inverse form, we have here the inverse. And now some of you already see this, right? If we now plug in this sigma here, right, we plug it in here, then we see that the mu, I hope I have enough space here, the mu, let me write it down here, the mu becomes beta times, we plug in our solution for the covariance matrix, here the -1, the inverse, here the phi transpose y. And now you see something, right? The beta inverse and the beta cancels out, right? So this here disappears. And what we are left with is that the mu becomes the pseudo inverse times y, right? So this is what we derived before. The mu, the mode of this distribution, in the case of alpha equal to 0, or becoming close to 0, becomes the pseudo inverse times the target vector. So indeed we see that this here also reduces to this normal equation we have seen before in the standard non-regularized linear regression by making alpha close to 0. And then finally, what we could also see is if we, for example, don't have any data points, right? So what will be the result if we don't have any data? Of course, the result should be the prior, right? If you have some prior knowledge about something, but you don't observe any other data, you don't have any other evidence, of course, it should be the prior at the end of the day. And this is also what you see here, actually, right? Because what will happen if n equals to 0, it essentially means that this here disappears, or this here disappears, this all becomes 0, and this becomes 0, which was our prior assumption that the weights are close to 0, right? Not surprisingly. And the same here, of course, right, for the covariance structure. If this becomes 0, then our covariance becomes alpha inverse times identity matrix, as we assumed for our prior distribution. Okay, so these are 3 nice observations. There's even a last one. So the last one is, we assumed here like an isotropic Gaussian for our weights. So we assumed that the weights are not correlated, so to say, right? We assume that we have off-diagonal 0 matrix here, right? We had here like diagonal elements, and all these were 0. So we had here these circles, so to say, okay? On the weights, right? The weights, they are not correlated, so to say. But what is interesting to note here is, while this might hold for the prior, we see that this might not hold for the posterior, right? So the posterior covariance in general is not diagonal. So we might have some kind of effects, correlations between the different weight vectors in this kind of posterior distribution, okay? So put differently, if we look, for example, at the space of weights, so let's say here's weight 1 and weight 2, right? So these are 2 potential weights we have, right? This is a space of weights we're expecting. So it could look like this, for example. Here's the mean, and here we might have some kind of distribution for the weights. Okay? So again, I'm repeating this a couple of times here. Be always careful which space we are talking about. So here the space of weights, right? So let's say we have a linear regression model where our data has like 2 dimensions. So we're interested in 2 parameters, for example, ignoring the bias here. So we have here weight 1 and weight 2, and we can show what are most likely weights. So here in the middle is the mode, so this is the map estimate. So this estimate for the weights. So for example, here it's, let's say, 2, and here it's 1. So this is, for example, the map estimate, but we can also get somehow like information about other potential solutions for these weight vectors. And they might be here like correlated in a specific way, even though in the prior we assumed something different, right? So also note here the shift, right? So the shift, this is here the mu, right? So here this center, so to say, this corresponds to the mu, which we have here, and this shape here, of course, corresponds to the covariance structure, okay? And this is talking about the weights, okay? How the weights might look like. Good. So this was the fully Bayesian approach, and now this essentially completes the big picture, right? We had the MLE first, then we had the map, and then we have the fully Bayesian, which, as before, gives you additional information. You can compute the expected value, which of course here will be the same as mu, but you can also compute like regions, and you can look at how much is the variance here, how much is the spread in the parameters. Do you trust the parameters because they are very focused here around the center, or is it very broad that you can't trust the parameter estimate? Okay. So then to the actual task which we then want to do, right? Because having the weights is nice and we can interpret these weights, just be careful with the correlation or causality, right? But at the end of the day, of course, we want to do predictions. We want to predict something. So giving some new data, X, new input, we want to make a prediction about the target Y, okay? So this was just the first step we just did, okay? What we just did was our learning phase. So giving our data, we computed the MLE map or even the full posterior distribution. This was our learning phase, so to say. We try to find the parameters. Now we want to do inference. We want to predict something for new data. We want to derive how it looks for new data. And here, this is what I also said for the coin flip. So the parameters we have in our model are just more or less like a means to achieve this, right? So the actual interesting part is it's not to have the W's, usually, if you're not going for interpretation, but the interesting part is having some new data and making a prediction here. So how do we do this? It's extremely simple again in this point estimate view, as you can imagine, right? Because now what we derived is, from before we derived already these distributions, which I already mentioned a couple of times. We have here our predicted mean, and we have here our learned or not learned covariance or variance information. Or to make it a bit more detailed, we again have here our predictive distribution. It's a predictive distribution because now we are caring about the y and no longer about the w. And how is this y distributed? We had derived it before. It's distributed according to the predicted value of our function, and we had here our variance term. Okay. So this is again the benefit of our probabilistic model. I said it already. We assume that our target, our y, follows this distribution. So of course a predictive distribution also just simply follows this assumption by plugging in the values we just have learned before. Okay, meaning we plug in either here the WML, or we plug in here the WMAP, and we plug in here the beta ML, and here we assume that it's given, right? We didn't learn it to make it not too complicated. Okay. So this is our predictive distribution. I want to draw it one more time. The big advantage, and now be careful again with the space. Now here's X and here's Y. It's no longer the W space, it's in the X and Y space. We can have here, for example, a line. And if we get a new data point here, new X, 1, we get here not only this point, but we are also getting here the variance around it, so to say. So this is given by these terms here. Right, we're getting here also additionally the variance around it. And this is how we can use it now in practice, right? Every time you get some new x's, you can transform it if you want. You multiply with w because this was your prediction model. This was your function. You get the mean of the Gaussian, you have the variance, and then this is the output of your model. So that's all. That's simply how we can use it in the MLE and MAP estimate. As you can imagine, we can also do it in a fully Bayesian view. Right, we can compute our posterior predictive distribution, right? Again, the posterior with respect to the prediction, so to say, we're interested in, right? So this distribution. And note again here that this does not include any W anymore. Here the W was just a helper to achieve this model, right? Because if we look at this part here, we need somehow like our W to do this, right? And this is why we compute the map on MLE. But actually we don't potentially want to do this even, and then we can go with a full posterior predictive distribution, right? You see here only X and only the old data and no W involved. So how does it look like? And here again, I just show you the result. The technical details are not important. If you want, you can look it up in the Bishop book. But here just again the core ideas. So what do we have to do? We have to do, or to solve this, we have to inject our parameter again. Right, you see here the W doesn't appear. Here we have the joint distribution where we have the Y and the W, but then at the same time we're integrating it out. We're marginalizing it out, so these two of course are equivalent. So injecting W and then getting rid of W, so to say. Okay? And then we apply, so to say, the factorization here. We have here first of all the W given the data, and then here we have the W and the condition and the Y here. And of course here the D is not important, so you can see that D here might be injected, but this is not important because once we know the W, the data is no longer important to make a prediction. This is a conditional independent structure which follows from our probabilistic graphical model. Okay, I can go back quickly here to make this very clear. So let's say we get a new data instance, xn plus 1, right? And we want to make some prediction about this yn plus 1, right? So we're getting this, and this is what we want to predict here, right? And of course we have here this connection, right? And also from the B and so on and so forth. So once this was anyway assumed given, but once this is known here, this is given, the prediction here is independent of this rest here, right? So this follows graphically from this probabilistic graphical models. You can intuitively think about this that since you have this already, these connections, you can cut them away, right? Because here the information is already flowing through something which we already know, okay? So if we want to make a prediction here, we have given this, we have given this, and we have given this here, then you see that everything is determined which goes in, so the rest is no longer important, okay? And this is indeed what we did in this step here. So technically, we would have both here in the condition, right? X nu and D, X nu and W and D here, right? But the D here is not important because once we know the W, we can make already the prediction here. So this is conditional independent. So given this with respect to D, okay? So this is our factorization. And the same here, of course, by the way, right? So here we don't have an X nu because for the X nu, we don't have this W. So this W is estimated based on this part, right? The X nu doesn't play a role here. Okay, so now we have reformulated this based on the conditional independent structure we have. And now we can, in principle, just solve it, right? This is what we know. This was our distribution from before. So this was here when we plug it in, right? A Gaussian. This is also a Gaussian as we have derived before. Actually, we didn't derive it, but I have shown it to you a few slides ago. This posterior distribution with respect to the W is also a Gaussian. And now come some interesting results again, right? So we here have a product of two different Gaussians and we marginalize it out. As it turns out, this is again a Gaussian. So this is very messy to derive. So I will just show you the solution. Again, you see the solution is something over Y, right? Because again, what are we interested in? We're interested in now in the posterior predictor. So we have here an X and we have here Y. And we have here again our line. And we want to learn something about along this axis, so to say, if we would draw it something like this here, right? It's like this Gaussian, which is stacked here in this direction. You're likely here, you're less likely here, you're less likely here, but most likely you're in the middle, okay? So this is the distribution over Y we are getting, the distribution of our target, okay? And now you see some interesting result. This is what I want to show you here. So first of all, you have this mean term. Okay, this mean term is not too different, not too surprising as before, right? You have here your transformed data, and you have here your mean, which was from this few slides before, right? The mean is given here, which would correspond to the map estimate. Okay, would correspond to the map estimate. So you see that this here is more or less the same as we have seen before. So this is W map. Okay, so W map times your transformed data. W map times your transformed data. Not surprising, right? Because the mean of a Gaussian is a mode and the mode is a map estimate. So here, this is what we are getting. So the prediction here, the mean prediction on the line, so to say, this is of course the same. Interesting is the second part here. Okay, the second part is here, this beta. Okay, fair enough. But then you see the X nu also plays a role. Okay, so we have our transformed data again, and then we have here this covariance we have seen before. Okay, so why is this interesting? Why is this different from before? You see that now the variance also depends on the data instance itself, right? You get a new X. Here, this is our new X, for example. And you see that the variance now changes. This is something we haven't seen here, right? The variance was some beta. Either we assumed it's already fixed or we learned it. But in any case, the variance was fixed, okay? So what does this mean, this fixed variance? It means if you would draw it, and let me draw a new plot here. If you would draw it, you have here your X and you have here Y and you have here your line. The variance is always the same, meaning you have here like something like a tube around it, which always has the same width, so to say, right? So the variance at every position is the same, right? So here it's a mean prediction. Let's say here this is 1 sigma, 2 sigma, 3 sigma. This is how likely you are expecting values here, right? Very likely here, less likely here, and even less likely here. But the tube has the same width, right? So the variance is always the same at every position. Here, this is not the case, right? Depending on where you are in the space, the variance might change, okay? And this is indeed a very big advantage of this full posterior solution if you really go with this full-blown version. And here I have some plots to make this more clear, and then you see the big advantage. So what do we see here? We see as before, like our input X and our output target. Here's the underlying true function, which we have seen before. It's a sine function, right? And here in these plots, we see different aspects. So first of all, we see, again, as before, like our observed data. Here we see just 1 point. Here we have observed 4 points. Here we have observed many points, okay? In red, we see our, say, the mean prediction, so to say. We see what I have always drawn here as this line, which means we are plotting here the mean, right? Because the line is the mean. This is what our function just predicts without this variance term. Okay, so this term is this line, and this is what we are plotting here. So you see very many different points in this plot. First of all, if you just have a single point, our prediction will be a line because you don't have any more information. What else can you do, right? If you get more data, you see that this function tries to approximate it well. If you have many, many data, you see, oh wait, that's nice. Our red estimated function, the mode, the prediction, right, the map here is already very nicely approximating the green function. That's one observation you see. The more data you have, the better is your estimate, which matches the intuition, right? As in the coin flip, the more outcomes of the coin I see, the better I represent the true function. At the beginning, it's close to the prior, flat, all zeros. Later on, it's becoming closer to the data, the more data I have. That's one nice result. Second result, and this is a big advantage of this actual posterior predictive, you see here the uncertainty. And at the beginning, the uncertainty is first of all very broad because you only have one data point, and specifically broad here in the outside. You see it's here small and here it's broad. More data, you see it's getting smaller, but here it's small and here it's getting broad where you don't have any data. Here many data, you're getting this kind of tube from before, right? You see now that this variance, the uncertainty, adapts based on what data you're looking at which position you're looking at. Because here you haven't seen any data, right? You have here large variance. Here you haven't seen any data, you have a large variance. Here you have seen some data, so the variance is getting smaller. Only in the limit, when you have many, many data points, you see that this is getting close to this tube I explained before, right? Here this tube has the same width everywhere, more or less, right? And this is what you would get from the standard map and MLE estimate. But in general, we have here the flexibility to have different kind of variations, so to say, depending where we've observed data or not. Which is, of course, also another helpful information, right? Because if you really want to make a prediction for this regime, but you haven't seen any data, of course, you should be more uncertain here than in the regimes where you have seen data. So that's a big advantage of using this actual posterior predictive distribution compared to the MLE and MAP estimates. Even though, again, I mean, for linear regression, of course, you can simply compute this. We have even here the closed form solution, right? It's not tricky to do this, but for more complicated models, this full Bayesian approach might not work. So finally, what you also see in this model, in this figure is, since we have now a distribution over the weights, we can, of course, also draw samples from this. I did this drawing before, a few slides back. Here, for example, right? We have the distribution over the weights, the posterior distribution over the weights, right? So we can, of course, sample from this distribution. So we are getting a weight vector here, a different one here, a different one here. So we're getting different solutions. And all these different weights, they correspond to different approximations we are making, right? Because a weight vector corresponds to a function, and the function is then something we can plot, okay? And this is what we did here, okay? So if you have the distribution, the posterior distribution over their weights, you can, of course, sample these weights, okay, right? You can sample from this posterior distribution, right? And you get, for example, one weight vector, you get another weight vector, you get a third weight vector, and so on and so forth. Right? You get 3 different weight vectors from this distribution, and every of these weight vector corresponds to one function. Okay? And this is what you are seeing here essentially. Here you see different realizations of weight vectors, which are sampled here essentially when you have 4 data points. And what you also see, and this links a bit now also a bit to this bias variance trade-off, you see, of course, that in these regimes, the function might differ. Right? Because you have here such a large variance, it could be that the function looks like this, but it could also be that the function looks like this. We are not sure yet, right? We are not sure how this function will look here, right? So it could go up or it could go down. And this is reflected by these different weight vectors or by the uncertainty, so to say, in this distribution, how this distribution already looks like. So here, at the moment, we still have a large uncertainty in the weight vectors. This is why we're getting here this kind of variation. Here we would be very certain, and this distribution would be very peaky. It focuses on a very specific set of weights, and all these models we can get, they would look always very, very similar. Okay, so you see that the more complex these models become, right, the more power we have and the more we can interpret. But already these models here, they are quite nice because at least they give you something like this tube-like uncertainty estimates, which is much better than the optimization point of view. Okay, and this then actually already finishes this first chapter on linear regression. So again, to wrap up, what did we talk about? We talked about optimization point of view of regression and probabilistic point of view, where we have this probabilistic model where you can think about that the output is like the outcome when flipping, not a coin, but flipping like a result from a Gaussian distribution. And then specifically, we have seen that this least squares error function, minimizing the squared residuals, corresponds to an MLE. And if we add regularization, meaning doing rich regression, we get a maximum a posteriori estimate under specific assumptions of the prior distribution. What we've also seen is that linear regression is not only capturing linear dependencies, but we can capture nonlinear dependencies by transforming our data, by applying here some basis transformations to it. That's more or less like trivial. We have seen that regularization or computing map estimates reduces overfitting. Right, and we can control this regularization strength, which is always good. We have talked about this bias variance trade-off also on a high level. And then last but not least, if we use this fully Bayesian approach, we get this data-dependent uncertainty, which gives you very much of information whether you can trust your predictions or not. So with this, I want to end this section. In the upcoming week, we will talk about classification. And again, we will have like a probabilistic interpretation, and you will see that classification follows a very similar principle than this regression, but just using a different model. With this, I want to end. Thanks and bye-bye.